just open movies.
Okay, let me show you what a double integral is, and I'll also explain how to compute it, and afterwards I'll try to explain what it means. So let's say we have 3x plus 2y, and you have dy dx with 0 to x and 0 to 1. So the generic form of a double integral looks like this. You have a function of x and y. You integrate by y and x, or it could be integrate by x and then y. Okay? All right, so let me first show you how it's computed, and then after you see how it's computed, we'll talk about its meaning. Okay? Okay, first, you just integrate as you would integrate a regular function. But just like partial derivatives where you consider the other one as constants, you do the same thing. You consider 3x, x as a constant where you're integrating by y. That's easy, right? So if you integrate 3x, what would you get if you're integrating by y? 3xy. It's just the antiderivative in the partial derivative version. So you could call it partial integration. Nobody uses that term, but that's what it is. If you integrate 2y, you get y squared. And then you're plugging in x and 0. And really, because you've integrated by y, these bounds, 0 to x, is really for the y values. So this x and 0 doesn't go into x, it only goes into y. Is that clear? You're plugging in these values, x and 0, into y only because you're integrating by y. So let's plug x into y, so you get 3x squared plus x squared, because the x times x is x squared, and x squared is x squared. And then when you plug in 0, if you plug 0 into y, it's 0, so there's nothing here. And then you're still integrating by x. We still need to integrate by x. And then, let's see, this is 4x squared. You're trying to integrate 4x squared from 0 to 1 dx. That everyone can do. If you've passed calculus 2, you should be able to do this. That's really easy, right? If you add 1 to the exponent, put the 1/3 in front, so it's 4/3, and you plug in 1 and 0. It's 4/3 minus 0, which is 4/3. That's the integral. Got that? Right, so that's how you calculate. Now let's talk about its meaning. All right. First, let me explain what this means. Y goes from 0 to x. If you just say y goes to if you say x goes from 0 to 1, that's easy to understand, right? X is a value that goes from 0 to 1 on this interval. That anyone can understand. But this is quite puzzling because y is not going from a number to number. It's rather going from, this is a number, but it's going to something that's related to x, right? And the way you should really understand it is that you should think about these as graphs in 2D, graphs in the plane. So let's think about what that means. Y equal to x is this. What's y equal to 0 on the plane? It's the x-axis, right? It's the x-axis. So you're basically saying that you're starting from this and you're ending up there. Okay? Where your x value is limited from 0 to 1. Okay? So while your x value is limited from 0 to 1, you're starting from here and you're ending there. In other words, what you're doing is you're starting when x is here, and you start from here and you end there. When x is here, you start from here and you end there, and there, and there. So it's like you're painting this region, starting from this end, and you're going up. Okay? Yes.
So it's the area?
So these values tell you how x and y moves, and the points x, y is moving in this region. It's not the area yet. X and y. So if you say x, y, it's a point on the plane, right? These x, y are moving in this region. That's what I'm saying. Okay. All right. Now, while that is going on, now let's think about what this quantity is. Now, this quantity is saying the following: dy times dx. What are these? dy is a very small increment in the y direction, right? Dx is a very small increment in the x direction. And if you multiply them, you end up with a very small area element. So think about it like this. If you have a very small increment in the y direction and a very small increment in the x direction, and if you multiply them, you get this very small area, right? Does that make sense? This is what we call dA. It's a very small area element. Okay? And then, if you multiply this area element by the value of the function, it will give you, it will be like a base area times the height, which gives you the volume of a column, very, very thin column. Now, to understand this, let me take you back to calculus 1. What did we do? Calculus 2. What did we do in calculus of one variable? So recall, in calculus of one variables, when you had integral of f of x dx from a to b, what was it like? You had some curve, the graph of this function, and it was from a to b. And what you did was dx was this very small length in the x direction. And what is x? Well, if this is x, the value of fx was this height, right? Fx is this height. And if you multiply this height by this dx, this length dx, if you multiply this times that, the height times base, then you end up with the area of this very thin strip. Okay? And then what you're doing is you're taking this very thin strip and you're moving the strips from A to B, and as you're moving along, you're adding them up. The integral means the sum. You're adding all these thin strips from here to there. That's what we did. And the end result was what? If you added all the area, what did you get? Huh? You get the area under the curve. That's what we were doing, right? All good? Therefore, here, it's the same story. See, in three-dimensional space, if you have a function of two variables, x and y, and if you call z equals to fx x, y, z is the height, right? So at each point x, y, if you plug those values in, you get the height at that point, right? And in the base, you have dx times dy, which is the base area, times the height, gives you this very thin column. And the volume of the column is given by f of x, y times dy times dx. Base area times the height. And then what you're doing is you're basically taking all those very, very thin bars and you're adding everything up so that you end up with the volume under the graph. Okay? So the meaning of this calculation, this 4/3, is it's the volume under the graph. So let me write that down here. This is volume under the graph of fx comma y equals to 3x plus 2y, okay, over the region this thing. Oh no, not that one. Over the region this thing. Okay. So over this region you have some graph, and you want to know the volume captured between this region under the graph. Okay. So again, comparing to what we had here, over here we had just the area under the curve, and it was area under the curve over the interval a to b. That's what this meant, right? But now, because we're in this three-dimensional space, the base is no longer an interval. It's rather a domain. It's a region in two-dimensional space. So you're trying to find the volume under the surface over this region. That's what it means. Okay? All right. Any questions so far? All right. So let me do another calculation, which may be easier for you to understand. Consider the following function. F of x comma y equals to 2 minus x minus 2y. Find the volume bounded by this surface in the first octant. So here's an example question. Let's try to figure this out. By the way, octant is just like quadrant in 2D because xy, xz, and yz, these three planes cut the entire space into 8 parts. We call them octants. And unfortunately, we don't have any agreement on which is the second or third octant. But we do have an agreement on what's the first octant. That's the case when we have all the x, y, and z positive. Okay? In that case, I want to know that the volume of the object enclosed by this one inside the first octant. Okay. To really understand what this question is asking, it's better to know the graph. So let's try to draw the graph. Graph is z equals to the function. All right. Do you know what kind of surface this is in 3D? Paraboloid? No, no way. Why not?
Oh, that was the first thing I thought of.
I mean, to get a parabola at some point, you need to square it somewhere, right? It's all first power.
Is it a surface?
What kind of surface? That was a question.
What kind of a surface?
Yeah, of course it's a surface. Graph of a two-variable function is a surface. Huh? What?
I don't know.
Really? Yes.
A plane?
It's a plane, yeah. How do you know? First power, yeah. It's a plane, of course. All right. So xy, let's talk about the xy trace. How do you get the xy trace? You set z equal to 0. And then if you solve for y, 2y is negative x plus 2, y is negative 1/2 x plus 1. So that's line with y-intercept 1 and negative 1/2 as its slope. So this will be 2. 2 will be the x-intercept. And then this is the one that's enclosed inside the first octant. Remember, first octant meant x and y and z are all positive. So if you only wanted the part of this that's in the first octant, this will be it will be this shaded area. Okay. Now, how about yz trace? That's setting x equal to 0. So z equals to 2 minus 2y, which is here's 2. And it comes down, so that's 1, and that's in the first octant. And then xz trace, that's z equals to 2 minus x, so it's like this, 2, 2, that's the graph. So here's what it is. Let's say this is x, that's y, that's z. I know that for z and x, the intercepts are 2, whereas on the y it's 1. And it's made up of these edges that's connecting these points, right? Here, here, here. And those triangles are each of these lines. 1, 2, 3. These are here. And then the surface, therefore, that we're talking about, z equals to 2 minus x minus 2y, are really the plane passing through these 3 green lines. Okay, so can you think about that surface? That's the surface. And then if you think about the part that's bounded by this surface in the first octant, it's the one that's inside the surface, right? So you know that it's this octant, this tetrahedron. All right, now let's think about the volume of this tetrahedron. That's, after all, that's what the question is asking, right? Okay, this length is 2, that length is 2, and the opposite side, this length is 1 on the opposite side. Okay. Now, do you remember how to get the volume of the tetrahedron? We learned that before. What do you do? I mean, you probably knew it when you were taking the first exam, right? But now you forgot?
No, it's the cross product. I'm sorry.
Yeah, it's triple scalar product. Okay, that gives you the volume of the parallel pipe. But then what do you do?
Divided by
1/6. It's the 1/6 of the volume of the parallel pipe, right? Volume of the parallel pipe containing this one is what? The parallel pipe in this case is actually a box, right? And box, the volume of the box is base times width times height, right? So length times width times height. 2 times 1 times 2, so it's 4. Right? And therefore the volume of this object is what? 4 times 1/6, which is 4 over 6, which is 2/3. Okay, so that's the volume. And now let me try to calculate this using a double integral. Let's try to do this using a double integral. And it's good because we already know the answer. Since we know the answer, if we calculate a double integral and get the same answer, then we can be more confident of what's going on, right? Okay, so let's try this. We're trying to calculate fx comma y dy dx, or dx dy. By the way, there are actually 2 ways to compute this using double integrals. You can do it by dx dy or dy dx. And I'll explain you how you can use either one of them. But for here, I'll just stick to dy dx. And then after this, I might show you how to change the order of integration. Okay? All right, so we'll go from dy dx, and this is what's happening. On the xy plane, the points are moving on this triangle, right? And over this, you have the function, this function. All right? So you're trying to integrate this function over this domain. Now let's actually write out the bounds. Fx comma y is 2 minus x minus 2y dy dx. And as I said before, you have to say y equal to something to y equal to something, because since you have dy here, you have to write whatever you write here and here really means y equals to that thing. Okay? Now, when you have dy inside, you're trying to paint this region in an upward motion. Okay? So imagine this situation. You're hired for a part-time job painting walls. Okay? And the guy who's giving you the job wants you to paint these walls in various geometric shapes. Okay? And the additional instruction is that you're only allowed to paint either going upwards or going rightwards. The upward case is when you have dy inside. The rightward case is when you have dx inside. Okay? So if you had dx times dy, they'll be painting rightwards. I'll show you after this. Okay? All right. So if you're painting upwards, then you have to say where your brushes begin and where your brushes end. So where does your brush begin?
0.
Y equal to 0. Very good. Where does it end? Where does your brushes end?
X.
No, that curve. That curve.
Oh,
What is that?
2.
1.
No, it's not a number. It's a graph. It's a graph. It's this graph. Your brushes begin from 0 and you end at this graph, right? What's the equation of this graph?
Y is equal to negative 1 half x plus 1.
This one.
That one.
This one.
Oh.
So it's negative 1 half x plus 1. And then, now after you've figured out how to paint it, you have to talk about the margins of x, the minimum value of x and maximum value of x. Okay? So what do you write?
2, 0.
0, 2,
2.
2. That's what it is, right? Okay, now let's actually do the computation. If you integrate by y, 2 integrates to 2y, x integrates to xy, 2y integrates to y squared. You're trying to plug in negative 1 half x plus 1 into y, and also 0 into y. And remember, these are only going into y because you're integrating by y, okay? Times dx. When this goes in here, twice of this is negative x plus 2. When you plug this in here, you multiply it by 2. Minus x times y is negative 1 half x plus 1. Minus negative 1 half x plus 1 squared. And then from this, now you have to plug in 0 into y and subtract. But if you plug in 0, there's nothing. So that's all you're going to get. And you're trying to integrate from 0 to 2. Now let's continue. Okay. Let's see. That's equal to 0 to 2. Negative x plus 2 minus 1 half. Actually, plus 1 half x squared, right? If you multiply negative x to negative 1 half x. and then minus x,
Wouldn't it be plus X? Oh.
negative
never mind.
x, yeah, negative times negative is positive, right? Okay, and then minus of this, well, minus of, this requires FOIL, so if you write this twice and FOIL everything, you're going to get 1/4 x squared, and you're going to get minus x plus 1. Okay, because if you square 1/2 x, that's 1/4 x squared. If you square 1, that's 1 squared, but then there's the cross terms when you FOIL with them out, right? So you get this negative x. Okay, and that's equal to 0 to 2, negative x plus 2 plus 1/2 x squared minus x plus 1/4 x squared plus x minus 1. Let's see, I guess this this one and that cancels.
Wasn't it negative 1/4?
Yeah.
Oh, thank you. That should be minus. Okay. All right, good. And then, let's see, so you get, for x squared, you get 1/4 x squared. Then you get minus x. You get plus 1. You still need to integrate by x, 0 to 2. That's 1/12 x cubed minus 1/2 x squared plus x. And then you plug in 2 and 0. If you plug in 2 to the third power, that's 8/12. 2 squared divided by 2 is minus 2 plus 2. So that's 8/12. And if you factor 4, if you reduce top and bottom by 4, it's 2/3. Is that right?
Yeah.
Same.
Isn't the first way easier?
Of course the first way is easier. Yeah.
So then when does it apply? When is it better?
Most cases you have to do it this way. It'll be like very few cases where you would do this.
Why? Because we'd be able to find the,
Yeah, I mean, it just happened that our case was a trapezoid, tetrahedron. The thing that we had was a tetrahedron, but usually it's not, right? Usually it's not. Okay.